Statisticians. Here we're going to look at another video where we're looking at the nonlinear relationships between paired data. And remember, in the beginning of our course, all we did was look at linear relationships. But in our last two videos, we were looking at some exponential relationships between two variables, right? And remember that an exponential curve looks something like this. If it's a positive exponential growth, it would look something like that. If it was some kind of exponential growth that was decreasing, you'd get something like this, right? And so sometimes the relationships we've seen between two variables are exponential. The form of that, the form of the equation for an exponential kind of growth, we wrote as y hat equals a times b to the x power, right? Where our variable is the exponent to some parameter b, and which is multiplied by a. So anyway, we saw something like this, and we saw that in order to take data and find this exponential equation to model it, we had to do a logarithmic transformation of our data, where if we had our original data set, which was x and y coordinates, what we would do is we would transform it by keeping the x values the same, but changing the y values to the natural log of whatever those y values were. And that what we'll end up finding is that the curve relationship that we seem to see in our actual data set, x and y, is going to become straightened, right? This guy ultimately straightens out that relationship, right? Now, we're going to learn about another type of nonlinear relationship that can exist today, something called in a power model, right? Power model. So in a power model, it's going to be based on a power equation. Now, power equations are ubiquitous. In fact, all polynomials are connected to power equations, right? So this guy right here, if I was to write this guy you would agree would probably look like some transformation of y equals x squared, right? And you can actually have like a cubic equation that you guys learned about, like, boo, there's a little cubic, and this would be some transformation of y equals x cubed. Well, any function of this form where you had as a model, if you had something like y hat equals a times x raised to the b power, right? Where now our variable is now being raised to a power, as opposed to in an exponential model where the variable is the power itself. In a power kind of equation like this, we'll get another way of trying to model some curved relationships. So these power curves can vary depending on whether they're even or odd functions, but you can also have rational exponents for b, right? So even if you think about it, even if you had this guy, and you were to graph this guy right here, this would be y equals x to the half power, right? That which is really the same thing as the square root of x. The square root of x is also a kind of power function, right? And so rational exponents can also be used here to model stuff. So sometimes we'll find that exponential models are the perfect way to model data. And sometimes we'll find that power. Now, what kind of transformation will give us a power model? We're going to see it's something similar to what we saw here with exponentials, right? It's going to involve a logarithmic transformation. So again, if we started with our data set, which was some x coordinate and some y coordinate, we're going to transform it, but this time we're going to actually do something to both the x and the y. We're going to take the natural log of both the x and the y, the natural log of x plotted against the natural log of y. And if we find that this guy becomes straight, right? This is straight now, then that means that there's a power relationship between our variables, right? However, if we find that this guy is straight, then we'll see that there's an exponential. Now, of course, these are only two possibilities. There could be other types of relationships. You can use sine curves. You can use all kinds of equations to model the relationships between variables, but these are the only two that we're really going to use in AP Stat, exponential and power models, okay? And both of them involve using logarithms to sort of try to straighten out our data. Let's look at an example, right? We saw a bunch of examples of exponentials. We're going to see that this guy's going to end up following a power model. But let's not get ahead of ourselves, right? So here we have some fun data. This is data on African antelopes, right? And I don't really know too much about African antelopes, but apparently we collected some data about the length and the midshaft diameters of their humerus bones. Now, in a human, the humerus bone is like connected to the arm. It's like your funny bone and all that stuff. So I guess these African antelopes have humerus bones too. I guess it's kind of maybe their front legs or whatever. So we have a bunch of data here, right? Where we're looking at the diameters of these humerus bones and the lengths of these humerus bones given in millimeters. And so what I'm going to do is my goal here is to try to figure out what is the real relationship between these variables? Like, what's the real relationship, right? And what kind of equation could I use to model this? Is it going to be a linear model? Is it going to be an exponential model, or is it going to be some kind of power model? We don't really know. Of course, I'm going to tell you right now, it's going to be a power model, but let's show that in fact it's going to end up being a power model. I just gave you a spoiler. Isn't that sad, right? So the first thing we're going to do is going to take all our data and we're going to throw it in our calculator right here, okay? So I did that earlier. If I go to stat edit, you'll see that I already put stuff in because you don't want to sit here and watch me plug in a bunch of numbers. And let's just first check to see what the data looks like using a linear model. So I'm going to hit stat. I'm going to go over to calc. I'm going to go down to option 8, and I'll do a linear model with L1 and L2. And I'll store the regression equation in, I'll hit alpha trace, and I'll hit Y1. I'll store that guy in, and so let me record this. Now, if you look here at this information, this already seems to suggest that I actually have a pretty strong positive linear association. Look at that, R is 0.997. If I wasn't paying attention to scatter plots and stuff, I would think that this is really probably the best kind of model I could get. So that's kind of interesting. But let's actually take a look at what the scatter plot looked for like this. And so I'm going to pick a scatter plot. I'm going to do L1 and L2, and now we hit zoom 9. Now, when I look at that, you might look at that and say, holy moly, that line seems to fit almost perfect through all those points. And I'd say that it's probably pretty close to being correct. But remember that in order to check if something really fits a linear form, a better thing to look at than just the scatter plot itself is the residual plot. So when I did that least squares regression line, when I created it, it actually created a list of residuals. So if I hit a second stat, and I go to make a scatter plot again. If I plot L1 against the residuals, and the residuals were stored in the list. So if I hit second stat, which is list, it'll take me down here, and I'll see here I've got all the residuals stored there in 8. And now if I make a scatter plot of L1 versus the residuals, I'm going to hit zoom 9. Whoa, baby. Look at that. I'm going to take a little picture of that. Let me copy that, and I'm going to paste that here. And I'm going to sort of move that off to the side, right? That's kind of nice. So there we go. This was the residual plot for, let me change that to, this is the residual plot for a linear model, right? And that shows that a linear model is not the appropriate fit. Since we see so much curve, clear curve in the residual plot, that means there's a leftover pattern that wasn't explained by the linear relationship. That means the linear model is out, right? We're not going to use this guy. Okay, so let's try an exponential model. Now remember, to do the exponential model, we're going to have to do a logarithmic transformation just of the y-coordinates. So I'm going to go over here to L3, and I'm going to hit natural log of L2 and paste that down. And now I've got in L1, I've got all the actual diameters of these humerus bones, and then the lengths, I changed into the natural log of the lengths. And so now I'm going to analyze those. I'm going to go to stat, calc, option 8, and I'm going to do a linear regression with L1 and L3, and I'll store the equation again. I'll store that into Y1, and let me hit calculate and Shazam. Now if I make a scatter plot of this, I'm just going to do a regular scatter plot of L1 and L3. So you're going to see the diameters against the lengths, and I'll hit zoom option 9. Now look at that. That actually seems worse than the original linear model. Do you see that the L1 versus L3 actually seems to be kind of curved, right? And that line doesn't seem to go through them well at all. Let's look at the residual plot anyways, just for fun. If I go here, if I go to second y equals, if I do L1 now against the new residuals, now as soon as I did that second regression, it calculated all new residuals, so that when I make a new residual plot, that one almost looks the same as the other one. I think literally it's like so close that it almost feels like I didn't bother making a new residual plot here. But I actually did. It's not actually the exact same thing. If you'll notice, there are some minor differences. And so this was our residual plot for an exponential model, right? And the exponential model involved that this was just x and y. This was x and the natural log of y, where y is the lengths and the diameters are x's. So this doesn't seem to be really much in a better fit than making a linear model. All right, so this guy seems to be out. This doesn't seem to model the relationship correctly. Let's go to now the power model. To make a power model, what we'll end up doing is, we'll go to stat, edit. We actually need to take the natural log of the x and the natural log of the y. So in L4, I'm going to hit natural log of L1. Now don't be confused, because I actually now have these flip-flopped. That what's going to be x is now L4 and what's going to be y is now L3, right? So I took the natural log of the diameters, which were my x variable, and I took the natural log of the lengths, which was my y variable. So now I'm going to be looking at the relationship between L4 and L3, right? So now when I do my linear regression, instead of using L1 for the x's, I'll use L4 because that was the natural log of everything that was in L1. I'll store the regression equation one more time. Alpha trace, option 1. I'll store that guy there. I'll enter and Shazam. Now look at that R. That R is ridiculously strong. And so I'm expecting that this got pretty gosh darn straight right now. And so let me make a scatter plot and show that. So let me do a scatter plot that was L4 and L3. Remember, the L4 was the natural log of x. L3 is the natural log of y. And I'll hit zoom, option 9 when I look, and oh baby, doesn't it look like that almost goes perfectly? But remember, the eye can deceive. The more important thing to look at would be the residual plot. So, all right, let's go to stat. Let's go to this guy. We're now going to plot L4. That was our x coordinates, but we're going to plot them against the residuals. And so let me do that. Let me hit option 9. And my friends, let's copy that guy and paste it in. This is a kind of residual plot I like to see, right? Notice that, remember that this time we plotted the natural, let me get back to a better color. This was the natural log of x plotted with the natural log of y. This was a power model, right? This was a power, and this guy makes me happy, right? Now, why does this guy make me happy? It makes me happy because when I look at it, you're going to see, and let me zoom in here, right? You see not much pattern at all. In the exponential and in the linear, we see clear. I mean, these are, I still hardly believe that these are different residual plots, but I do know that they are, but they are so gosh darn close, it's crazy to me. But both of them have a distinct pattern that's no good. But this power model, I mean, maybe I see a little bit of a pattern there, but it's much more minor of a pattern at all than what we would have seen in our power model, or excuse me, in our exponential. So I'm going to say that there is a power relationship between these two variables, right? If I want to make a prediction of a length from of the length of a humerus bone from the diameter of a humerus bone, I'm going to use the power model. So I'm going to go back. I'm going to go back and take a look and see what did my calculator actually give me when I did that linear regression. I want the actual equation itself, right? And so here we go. The equation given to me by the calculator, and let me rewrite this guy. I'm going to zoom in just a little bit, right? The equation given to me by the calculator was, remember, that's had to do with natural logs. This is the natural log of y hat, right, would equal that would be 3.18. So let me use a different color there. 3.18206.3. Now notice I don't like rounding very much here. And then what do we got here? Plus was our next variable. We had 0.659927, and then we had now notice that this isn't x. This is going to be the natural log of x, because remember we took the natural log. Actually, let me do that in another color. We took the natural log of x and we took the natural log of y and create our model. So in place of the y and the x in this equation, we actually have to write the natural log of x and the natural log of y, right? All right, so this is our model. Now we could prove that this would end up becoming a power equation, and I maybe I'll do that in just an addendum to this video. But for now, we'll just see that this is the model that we can use to make predictions, right? And let's just see. Let's just test out and see how we could actually use this equation to try to model the relationship. Let's say I encountered an antelope and I found that its diameter, right? So it's X. I found that the diameter was something like, I don't know, 47 millimeters in its humerus bone. And if I take a look at this chart, 47 millimeters would be like right about there. So if I had to guess, what would be the length of the humerus bone that had a diameter of 47 millimeters? I mean, just by looking at this chart, I'm guessing it's somewhere in this 300 to 323 range. But let's see what this actual equation would predict. So if I want to use this equation to make a prediction here, then what I'll do is I'll plug in 47 for X, right? So I'll have everything else written here. I'll have 3.182063 plus 0.659927 times the natural log of this number 47, right? And that's what I'll actually plug in. And so let me go to my calculator. And this is going to be annoying to type in. There are quicker ways of doing this, but I'm going to do it the long way. 3.182063 plus 0.659927, if I could read my handwriting, yes, times, now remember this is the natural log. I'll hit the natural log button, the natural log of 47, right? Boom. And I got, okay, this comes out to being apparently 5.7228 approximately. All right, now remember, what was that? That was the natural log of the predicted y-hat. So this is not my prediction for the, excuse me, I apologize for the length of the humerus bones here. But my prediction, the natural log of my prediction is equal to this value. So if I want to get the actual prediction for y hat, remember I'm going to end up doing e raised to this power. E raised to the power 5.7228. And so what would that be? Now I'm going to go in my calculator. Whoopsie, where did you be? I'm going to go in my calculator. I'm going to say, okay, my calculator, do e raised to this power here. And I got 305.78 approximately. So let's see here. Does that make sense to me? Let's zoom out a little bit. Remember when, just by looking at this chart, there was a ridiculously strong relationship going on here. And when I looked at where 47 would be, I thought it would be something sort of in between 300 and maybe 323. I got a prediction of 305.78. Do you think that's a good prediction? Heck yeah. I think that's probably pretty strong. And that's how we would use these models. Notice it's not necessary, just like I was talking about in our last video, it's not necessary to take this equation and to convert it over into something that actually looks like y equals a times x to the b power. It's not necessary to do that. You can actually work with the model just in terms of keeping the natural logs and such. And just a quick follow-up video to this, though, I will show that if I was to simplify this guy mathematically, it will end up creating an equation in this form. Okay? So hope this was helpful to you as we compare linear models and exponential models. Linear, exponential, and power models for the pairs of relationship. The real key for you knowing which model is the appropriate model is to look at the residual plots and see which one has the least pattern. And remember that, to generate these guys, it's all a matter of doing certain logarithmic transformations. For a regular linear model, you just keep your x's and your y's. For an exponential model, you make sure that you take x with the natural log of the y, and the power, you take natural log of x, and you take the natural log of y. See which one's straightest using the residual plots, and you'll be good to go. Have a beautiful day. Catch you on the flip side. Giddy the heck up.